Welcome back to the University Utara Malaysia School of Computing. I am Dr. Ala Jabbar Al-Maliki, and today we transition from the theory of cryptography into its practical, real-world construction. Banking networks, Wi-Fi routers, and cloud infrastructure process millions of transactions a minute. Protecting that data requires encryption protocols that can operate at incredibly high speeds while remaining mathematically unbreakable. This diagram illustrates symmetric encryption. Because a single shared secret key manages both encryption and decryption, the system operates very efficiently. From here, the architecture branches into two distinct operational models. On the top path, a stream cipher encrypts data continuously, processing it one bit or byte at a time. On the bottom path, a block cipher processes information by snapping it into fixed-size 128-bit rectangular chunks before applying the mathematical algorithm. Determining whether your system should process a continuous flow of bits or manage rigid blocks is the first decision you will make when engineering a secure communication protocol. Here is the mathematical engine of a stream cipher. It operates by taking a stream of plaintext bits and combining them with a pseudo-random key stream. By passing them through an XOR logic gate, the system outputs ciphertext fast enough for real-time video or voice communication. Block ciphers operate differently. Because most messages are much longer than a single 128-bit block, the encryption protocol requires a strict set of rules, called a mode of operation, to dictate exactly how multiple blocks interact with each other. Look at this image encrypted using the simplest rule set, electronic codebook, or ECB mode. Under ECB, identical blocks of plaintext always produce identical blocks of ciphertext. The data is technically encrypted, but the original repeating silhouette remains entirely visible. Now observe cipher block chaining, or CBC mode. This formula forces every new block to mathematically depend on the ciphertext of the previous block. This chaining action destroys any repeating patterns, turning the image into randomized noise. The strongest block cipher in the world provides zero protection if it is deployed with an operational mode that leaks the underlying structure of the data. This timeline tracks block cipher standards. The original data encryption standard, or DES, relied on a 56-bit key. That length is entirely insufficient today, crumbling easily under modern computing power. Running the algorithm 3 times, known as 3DES, was a highly inefficient patch that severely reduced processing speed. To solve this, the Advanced Encryption Standard, or AES, was introduced. It expands the key size up to 256 bits and utilizes a streamlined substitution-permutation network, executing multiple rounds of substitution and shifting to secure data rapidly. Combining the mathematical structure of AES with dedicated hardware acceleration on modern CPUs makes it the mandatory baseline for securing hard drives, Wi-Fi networks, and cloud storage. Encryption hides information. A hash function verifies it. This diagram shows a massive multi-page document and a tiny single word dropping into a hashing algorithm. Regardless of their original size, both output uniform 256-bit strings, acting as a unique digital fingerprint. Watch the input carefully. By modifying just one character, changing a capital O to a lowercase o, the output violently scrambles into an entirely different string. This extreme sensitivity is called the avalanche effect. Consider this scenario. An attacker creates a malicious file that generates the exact same digital fingerprint as a safe file. Which mathematical property of the hash function has failed? That is a failure of collision resistance. Researchers successfully executed collision attacks against MD5 and SHA-1, rendering them obsolete. Today, verifying digital certificates and blockchain ledgers requires the collision resistance found in the SHA-256 and SHA-3 families. Hash functions are also used to store passwords. However, storing pure hashes allows attackers to crack them instantly using pre-computed databases called rainbow tables. By adding a random data block, a salt, to the plaintext password before hashing it, the final output becomes completely unique to that specific user. Storing user credentials without pairing a strong hashing algorithm with randomized salts guarantees a successful data breach. This matrix summarizes your operational framework. Implement AES 256, the SHA-2 and SHA-3 families, and modern modes like GCM. avoid DES, MD5, SHA-1, and ECB mode under all circumstances. For your upcoming assessments, review these exact mechanics: the structural differences between stream and block ciphers, the mathematical advantages of AES over DES, the 4 required properties of a cryptographic hash, and finally, the mechanism of password salting. Mastering these concepts allows you to transition from studying theoretical cryptography to actually engineering secure systems. Review your study materials, and I will see you in Chapter 7.